started, I'm going to do a very brief review and keep going. Also, just a forewarning, you know that food and drink are not allowed in any rooms that have the black tables, right? Up to this point, I haven't been enforcing that harshly, but we're going to start doing stuff with chemistry on Wednesday after class. And so starting after class on Wednesday, I'm going to be enforcing no water and stuff because it's for your safety. Okay? So I want to make sure people know that I'm actually going to start trying to be more vigilant and making sure that people aren't doing stuff to harm their health. Okay, we have a test tomorrow. Thanks to the prompting of Caitlin MacArthur. I have the questions for review questions to help you prepare the homework and give you a little extra credit. And I have the equation sheet there on Moodle for you to enjoy, to take comfort in. The topics we're covering are just chapters 22, 23, and 24. So chapter 22, magnetism. So we have the causes of magnetism, two fundamental causes. One is it's an inherent property of materials, and the other one is that a current will create a magnetic field. And these magnetic charges do not come in monopoles, as far as we know. They only come in dipoles. That is, if you have a north, you always have a south. What happens if I take a magnet and I cut it in half? So the north was on one side and the south was on the other. I just have two dipoles now. Because the north wasn't just because there was north type material, it's because you had north pointing that direction and south the other direction. And so each piece had both. Magnetic field lines come out of the north. So the magnetic field lines come out of the north and go into the south. And what do they do when they go into the magnet? They go through. Right? That was different than our electric field lines. Our electric field lines started or ended at the charge. With magnets, they always do loops. And that's a result of the magnets not having a monopole, always having the dipole. So they make loops. What happens if I bring another magnet and I put a magnet, for instance, like this, so it has north pointing that way? What's going to happen to that magnet? It's going to what? It's going to have a torque to make it rotate so that the magnetic field lines will do what they're supposed to do, come out of the north and go into the south. So it should have a torque to make it align. Now, we never talked about the actual force between two magnets. We said that opposites attract and likes repel. That is, north attracts south, north repels north. But we didn't talk about, and we're not going to talk about, the actual strength of the force between two magnets. That said, we should keep in mind, because north is attracted to south, if I put a compass on Earth, the north-seeking pole is defined as the pole that goes toward the Earth's north pole. And we call that north-seeking pole north. So the North Pole, the north-seeking, what magnetic pole is it seeking? South. The north-seeking pole is seeking a south pole. Makes no sense, but it's because they didn't really understand what they were dealing with when they named it. So that means the Earth's north geographic pole is a south magnetic pole that the north of your compass is pointing to. Okay. Yes.
I thought I read in the book that magnetic field lines are always tangent to the field. Will you explain that? Or did I read that wrong?
That's not going to be right.
Okay. Is there anything related to that?
Electric field lines, well.
It does say that.
Well, okay. I was thinking perpendicular. That would be then in the I thought it was perpendicular, which would be wrong, but it would be redundant because they point the direction of the magnetic field. right? That's what it means. So I maybe not redundant, but it's the magnetic field points the direction of the magnetic field lines
Okay, at each point on.
at any point. Yeah, you're right. I was thinking like with electric field lines are perpendicular to equipotential lines, but that's not tangent. That's perpendicular. Mahalo.
I think I also read in the book that magnetism is always caused by moving charges.
Yeah.
So I was wondering about naturally.
Yeah, it's not always caused by moving charges. In fact, remember we talked about the spin, like the spin of an electron. They named it spin because that's what they assumed it was caused by. But now with our understanding of an electron, we know that it's not even possible that the magnetic moment of the electron is created by motion. And so it has to be an intrinsic property. So it was thought that it came from motion, but they thought wrong. Okay. Make sure you know your right-hand rules. How many right-hand rules have we learned? 3. We've learned 3. We had the first one was for cross products. We had it in torque, and now we had it again with magnetic field and forces. So we had torque equals R cross F. It came back to us because when we start talking about electric motor, we're talking about the torque created by the electric motor, and we had to use that equation. Then we have the same rule. Magnetic force is equal to QV cross B or IL cross B. And so whenever you use this right-hand rule, remember that you have your index finger in the direction of the first item. So that would be in the torque equation, R is the first item. In the force equations, either the velocity or the length of the wire is the first item. Keep your thumb perpendicular to index finger. Allow your fingers to bend from pointing the same direction as your index finger to point opposite it, the way your right hand bends. Don't use your left. And your middle finger needs to be aligned so it points the direction of the second one. And then your thumb points the direction of the answer, of the result. So make sure you can do that. That's the first right-hand rule. The second right-hand rule, when you have current going through a wire, put your thumb in the direction the current is going, wrap your fingers, and the current or the magnetic field goes around the wire in the direction your fingers wrapped. Yes?
In which direction does the force go for that one? Either
That's a magnetic field. That's not a force. That was only current creating magnetic field. Yes.
Okay.
Yeah.
So in that instance, you'll have the wire and you wrap your fingers around,
Mhm.
and it'll ask like which if you're looking at it from this perspective.
Yeah, from this point.
Now, do your fingers wrap all the way?
They wrap around, so it's making a circle. So at any point you do the direction that your fingers would wrap around. So if it was okay, so with the current going up, if it's toward you from the wire, then the fingers are going to your right.
Okay.
If it's away from you, then they're going to your left. And if it's on your right side, then it's going away from you. If it's on your left side, it's going toward you.
And on a solenoid, you can have the current being your thumb curling and then your
Okay.
fingers going straight.
The third one is for a solenoid. And for the solenoid, you make your fingers the direction the current is wrapping in the solenoid, and then your thumb is the direction of the magnetic field in the center of the solenoid. Because outside is going to be the opposite, right? Because it's going to go up and around like that. So you have to remember it's in the center is what the thumb is doing for the solenoid. And that third rule is really just applying the second rule. It's, you could go all the way around like this 100 times, or you can just do the once.
Will you walk through the components just one more time of the index thumb?
Okay, so you have your right hand. I will do the best of writing my right hand. Here's my index finger. Here's my middle finger. And my thumb is pointing out with this, right? That I'm not a good artist, so I'm just doing the directions. And so if I have something that is like A cross B equals C, then it's always going to be the first item in the cross product is the index finger. And the second item in the cross product is the middle finger. I should have used color coordination here. And the answer is the thumb. So regardless of which cross product equation it is, it's the same rule. Okay, we have electric motors. What makes an electric motor work? You have current moving in a wire. That current moving in a wire has a force, as given by force equals IL cross B. And then you take the forces in the wires going around the loop, creates torques that make it rotate. And so, of course, you'll be given the equation for, the torque is equal to NBA is it NBA? Yeah. Sine of omega t. I think that was the equation for the torque. Right? You'll be given the equation. You don't have to know that. But you should know about which direction the torque is going to be and how it's caused, as well as being able to use that. The Hall effect was the effect that if I have current going through a wire and it's in a region with a magnetic field, there's going to be a force on that current. So force is equal to Li cross B. There would be a force to make my charge carrier move up. And this Hall effect is actually useful because it makes the charge carrier move up. It doesn't matter if it's a positive charge going left or a negative charge going right, it's still going to move up. And so using this Hall effect, you can actually determine what's carrying the charges. So if you do this with a piece of copper wire, you find that the charge that moves up here is the negative charge, and so it was negative charge carriers. But if you do it with something like a silicon wafer, depending on how it's doped, you might have positive there or negative there. If you have positive that moves up there, what does that tell you? If it moves the charge carrier to the top and the top is positive, what does that tell you? If A equals B and B equals C, what is A equal to? C. Okay. So if this Hall effect makes the charge carrier move to the top and the top is positive, what does that tell you? That the charge carrier is positive. But I've been saying all along that the protons are the positive charge and they're fixed. And so what we say in physics and engineering is that it was hole migration. And what's a hole? It's an absence of negative charge. It's a place where you should have a negative and you don't. And it's these places that are missing electrons that's migrating. So electrons are hopping, and it's the missing electron that's what is moving. Which is kind of convoluted, right? But we do have a positive charge carrier in that case. Okay, then we have Ampere's law. We had learned for the previous test that with Gauss's law, if we have a charge, it makes an electric field. Ampere's law tells us we have a current, a flowing charge, it makes a magnetic field. And so Ampere's law, you should be able to use it. It says that the circulation, that is the sum of the magnetic field dotted to the sides, that's supposed to be a delta L vector, of a loop, not a physical loop, but one you're using for calculational purposes, is equal to mu naught multiplied by the current enclosed by that loop. So that was Ampere's law. By now we've learned from chapter 24 that Clerk Maxwell, added an addition to that said, okay, if you have a changing electric field, that's equivalent to having a current. And so it also had a changing electric field, electric flux, it turned out, part to that. So you'll have both, should have both forms on the answer sheet. Well, If you have the second one, it includes the first one. So you'll probably have it plus mu watt, epsilon aught. Change in magnetic flux over change in time, I think it was. I don't have this perfectly memorized, but I think that's right. So that's Ampere's law. Make sure that you can apply Ampere's law if you're told to use it on a long wire where you have a nice cylindrical symmetry, or on the solenoid. Remember, with the solenoid, we used a loop that went through the center and then went down infinitely far so that the magnetic field strength is 0 if you get infinitely far away. The magnetic fields are going to be perpendicular to the sides, and thus the only place that B is parallel to the length is in the center. And then we use that to find the strength of the magnetic field inside of the solenoid. Finally, from this section, force between two current carrying wires. Make sure that you know, okay, if I have current in a wire, that makes a magnetic field. I can use my right-hand rule to determine the direction of that magnetic field. And if I have a second wire that has current passing, then I can use my force is equal to IL cross B to find the force on the second wire due to the first one. So make sure you can go through that process. Now chapter 23. Chapter 23, we were looking at how motion could create a voltage. So we had Faraday's law of induction that said the induced EMF is equal to minus N change in magnetic flux over change in time. We did lots of things with that. We saw how if I have a moving wire, it's going to create a voltage difference for the moving wire. If I have a moving loop, it's going to create a current in that loop that depends on the resistance of the loop. Lenz's law. What did Lenz's law tell us about? The direction. It tells us that the induced current is going to be the direction to oppose the change in magnetic flux. So if the magnetic field is getting stronger, then the induced current is going to be in direction to make a magnetic field opposing it. If the magnetic field is getting weaker, the induced current is going to make a magnetic field to make it stronger. And I say weak or stronger if you're changing angles. That's why we say the flux, because it's technically the flux. You can have a constant magnetic field, but you change your angle so the flux goes down. It's going to try to make a magnetic field to augment it to keep the flux constant. Eddy currents. Remember the examples with eddy currents, things like this. Make sure you understand why you have those eddy currents. Electric generators are just an example of using Faraday's law of induction. Transformers. What do transformers work on? They work on alternating current. If you have DC, it won't work. You will assume, unless told otherwise, that it's a perfectly efficient transformer. For a perfectly efficient transformer, you have no energy loss. So power in equals power out, which means V1 I1 equals V2 I2. And given that V1 over V2 is equal to N1 over N2 for a transformer, I know that's horrible contrast. I'm going to change that last one. Then using that power is equal, you get the same ratio is equal to I2 over I1. And so the transformer will step up or down voltage, but if it steps up the voltage, it steps down the current, so that the power remains constant. Finally, in this chapter was inductors. We learned about a transformer is a mutual inductor. You have two wires that are separated from each other. You can have a ground on one wire that's different from the ground on the other wire. That's a big reason we use transformers. In electronics, you have something coming in and you want it to not share the same ground with what's going out. So you can use a transformer and you remove the ground. So it's a mutual inductor. Inductance means that you have a magnetic field produced by the first coil, and then that changing magnetic field produces a voltage in the second coil. That's the mutual inductance. An inductor is a self-inductor. You wrap a single wire You put current through it, the current makes a magnetic field, but the change in magnetic field induces a voltage. And so that's what an inductor is. Same idea as a transformer, except for it's just one wire. So make sure you can work with inductors. And of course, with inductors, we have the inductors in a circuit and transient circuits. Transient circuits work essentially the same as with capacitors, except for the time constant was L over R, R over L, instead of L over R. Okay. I don't remember offhand. Instead of RC. So you have, in all cases for the transient circuit, the voltage as a function of time is equal to the voltage you start with minus the voltage you end with, e to the minus t over the time constant plus the voltage you end with. And likewise for current, if you just replace V with I, it's also correct. So you just need to find the time constant, and you need to find the initial and final voltages, initial and final currents, and you have everything you need. Transient circuit is moving from one state to another state. AC circuit is continually moving back and forth. And for AC, we restrict ourselves to exclusively sinusoidal. That's an L. And in that case, remember, we had all of our stuff we learned about in lab, the impedance, the reactance, XL is equal to omega L, XC is 1 over omega C, Z is equal to the square root of R squared plus XL minus XC squared. Make sure you remember all of those things from lab. Yeah, I'm not going to have you draw a phasor diagram, so you don't have to worry about can I draw it, but make sure you understand how these things work. And many times that phasor diagram, the reason we do it is because it helps you. Final chapter, Maxwell's equations. How many equations were there before Maxwell started? I don't know. How many did he get it down to with his first publication? Down to 20. How many did he get down to in the end? 4. Now, of course, 4 is the number that's important. That 20, I mentioned it for historicity, so you understand what he did was not minor. But he got down to 4 equations to describe all of electricity and magnetism. And so these are the 4 equations: Gauss's law for magnetism, Faraday's law of induction, and Ampere's law with his displacement current. Those 4, what's important is that they explain everything. In electricity and magnetism, they tell us that a changing magnetic field will produce an electric field. A changing electric field will produce a magnetic field. And in fact, that electric and magnetic fields by themselves can support waves. So this is not a water wave. It's not a sound wave. It's an electromagnetic wave. It's a wave with electric and magnetic fields. And for those electric and magnetic fields, the direction of the electric field is always perpendicular to the velocity direction. The direction of the magnetic field is always perpendicular to the velocity direction. And the direction of the electric field is always perpendicular to the direction of the magnetic field. So they're mutually exclusive. So they're always going to be perfect right hand. And so you have that relationship that the electric field is minus V cross B. Or if you want to make it so you don't have a minus sign, how can I write that same equation without a minus sign? B cross V. And finally, I think this is finally, the electromagnetic spectrum. Electromagnetic spectrum is the range of frequencies and wavelengths we have going from radio waves up to ultraviolet. Make sure you have a reasonable understanding of that, especially where the visible section is, because the visible section is what we're studying now and moving forward. And we have the relationship that frequency multiplied by wavelength is equal to C. What does C stand for? Speed of light. More specifically, it's the speed of light in vacuum. So frequency times wavelength is equal to the speed if it's not in vacuum. This here applies to if it's in vacuum. Most of what we do, we talk about in vacuum. Air is very close to vacuum. So if it's going in air, we'll still use that relationship. If it's going through water, speed of light in water is, I think it's about 2/3 the speed of light in air. Speed of light in diamond is really slow. Well, let's do it right now because we're ready to move on to the new material. We have this parameter that we use to relate the speed of light in different materials, and we call it the index of refraction. Now, I'm going to be talking about refraction as soon as I go forward in the slide. The index of refraction N is defined as the speed of light in vacuum over the speed of light in whatever my material is. So for water, N of water is equal to 1.5. That's not right, 1.33. So if N in water is 1.33, what's the speed of light in water? First, solve the equation for V. So take my index of refraction equation. What does it solve for V? C over N. It's asking me C over N of water, which between good friends, I'm just going to put 3 times 10 to the 8 meters per second. 1.33, that's also written as 4/3. So 3 times 10 to the 8 divided by 4/3 is equal to 9 and 4. What is that? 2.2 at what? So there's the speed that light travels through water. Now let's take something peculiar, diamond. I believe it's 2.42 is the index of refraction for diamond. What's the speed of light in diamond? I put meters per second, forgot the times 10 to the 8. So light goes very slowly through diamond. That's a big part of why diamond is pretty and sparkly, because light goes so slowly through it. And we'll learn about that today. Question?
I had a quick question about one of the review problems had 2 coils next to each other. One was vertical and one was horizontal, and what was the induced magnetic flux between the two? And it was 0, but I'm just wondering about why that is. On a closed surface.
If you have the coils like this and like this, that's going to be correct. It sounded like what you described was like this.
Yeah.
Like this, it's actually not. Because if it's like this, you're going to have a certain amount of magnetic field that comes out like that, right? And in that case, it's not 0. But if it was at the center, then nothing would have gone through that lower one.
So it was assuming that it was all.
Yeah, it was assuming that it's staying all horizontal in that range. And of course, if it had also, there's another case where their answer would be correct, and that would be, if it was like that, their answer would also be correct. Because then based on the symmetry, you'd have as much going down as coming up. So it's a question that, was the geometry like this?
I think so.
If it's like this, then they were imprecise. They meant like this. So they meant for a horizontal magnetic field, which makes no magnetic field going through. Okay, so we've talked about reflection. We had 2 types of reflection that we focused on: specular or mirror-like reflection, and diffuse, which was spread out. And the difference was the smoothness of the surface. If we have a surface that's smooth to within the size of the wavelength of light, then we're going to have a specular reflection. But if it's rough on a size bigger than the wavelength of light, then we're going to have a diffuse reflection because the surface looks like it's, all different directions. So light gets reflected all different directions. If I have light hit glass, normally we think, well, light goes through glass, right? But if you pay attention, if you wear glasses, for instance, you notice that light also reflects off of the glasses. And it's about 4% of the incident light that will reflect off of a piece of glass, and about 96% goes through. Those are about, it depends, it has to be normal for these to be the right numbers. It depends actually on the index of refraction of the glass. There are different kinds of glass. You may or may not be aware of this, but we have glasses with indices of refraction that are a little bit less than 1.5, up to glasses with indices of refraction that are above 1.7. And you're going to have more reflection if it's a slower speed, so a higher index of refraction. So now we're going to look at what happens to the light that goes through the glass. And when it goes through the glass, we're going to have what we call refraction. Refraction is a bending of the light when it goes from one material into another. Now there's something that's important that we learned back with sound waves and waves on a string. If I have a wave that goes from one material to another, the frequency has to stay the same. That is, if I have two pieces of rope that are tied together and I'm going up and down on one side, on the other side where it goes from one rope to the other rope, it has to have the same frequency of going up and down. Why? There's a really easy answer to why. I have a knot holding the two pieces of rope together. If one side of the rope is at one frequency and one side's at the other, instead of going like this at the knot, I'm going to be having them going, not staying together. But the fact that the knot holds them together means they have to go up and down at the same frequency. So frequency has to stay the same when you go from one material into another. But if you go from one material into another and the speed changes and the frequency stays the same, what else has to change? The wavelength. Because we know frequency multiplied by wavelength is equal to the speed. And so you can have frequency is the same as the speed over the wavelength. So if the speed goes up, what's going to happen to the wavelength? It's also going to go up. If speed goes down, the wavelength gets shorter. We can also write, since speed is equal to the speed of light in vacuum divided by n, then this is equal to c over lambda n. So lambda, the wavelength multiplied by n, the index of refraction, has to remain constant when you go from one material into another. So here's light going into glass. So starting in air, you see it has air written down. And then it goes into glass. It has glass. Because glass has a slower speed than air, the light has to slow down. So the wavelength has to get shorter. Because the wavelength is shorter, that means the separation between wavefronts is smaller. So as the light comes in, I always think about this like, go to my sister's house in Huntington Beach. You've got the nice little concrete sidewalk that everybody's jogging on, or riding a bicycle on, or skating on, or you can rent the little four-wheeler things, right? The little bicycle four-wheel things. Well, if you're riding that little bicycle four-wheel thing, and you're not paying attention, true story, my brother-in-law was walking down the bicycle thing, and there were some girls playing volleyball. He looked over them, and he walked right over this kid's scooter. Kid's mom just about had a heart attack. She was wanting to fight us all. And yeah. Anyway, so if you're not paying attention, and you go off the side, and one tire goes into the sand, how's the speed of a tire rolling on concrete compared to the speed of a tire rolling in sand? Concrete, it'll roll faster. You've got more resistance to it going. what's going to happen to your direction when that tire drops into the sand? You're going to turn so that you're heading more directly into the sand. That's exactly what light does. In fact, not tomorrow, but a week from tomorrow in our calculus class, we will talk about the brachistochrone problem, I think I said that right, about light traveling the shortest path. So the light bends into material that goes slower. It'll bend away from material that goes faster. So when the light goes into the glass, it's going to bend, so the angle of transmission here, we call this the angle of refraction. You have to go to the fourth letter to differentiate reflection from refraction. The angle of refraction is closer to the normal than the angle of incidence. Now, I'm not going to do the derivation for Snell's Law. Snell's Law is the law that tells us about these, and you can derive it both the way we're going to do in class a week from tomorrow with calculus, or you can do it with geometry here, just saying, okay, I have similar triangles. And with these, well, they're not similar, I said the wrong thing, but I have triangles I can compare. I have the wavelength is the opposite side on these two triangles, but different wavelengths, one in air, one in glass. I have a same side here. Let me change the color so it stands out. That's the same for both triangles. But then I have those two angles, theta incidence and theta reflect or transmitted. Shoot. So all the geometry is actually written out on this page. It's saying that the ratio of the angle, sines of the angles is wavelength over this distance here that's in blue. And it gets you down to this relationship that says the index refraction in medium 1 multiplied by the sine of the angle between the normal and the light ray in medium 1 is equal to the index refraction in medium 2 times sine of the angle between the normal and the light ray in medium 2. It doesn't matter if you're coming or going. That's Snell's law. That tells us how the light is going to refract. What did the word refract mean? Bend. Now, let's have at least a little fun. I have to do one more thing before we do this. And that is turn off this. Okay, so there I have a little laser thing with light coming out. And I'm going to have that light go into a material. So here, the light goes into this block. What do you see happen to the light as it goes through the block? Is it loud? Basically straight. You see basically nothing. Well, now I'm going to rotate this. Okay, now we have a lot of things going on. Let's pay attention to the light that went through. What happens when it hits this surface? It bends up. Why does it bend up? What do we call that process? Refraction. Because I tilted it so the normal is now going this direction, the light bent toward that normal. Because it's going slower in the plexiglass, the polymethyl methacrylate, the lucite, than it is in air. When it comes out, so the light's going like this when it comes out, what direction does it bend? It goes away from the normal. And in fact, because it's parallel surfaces, it comes out parallel again. We can also see this light here. What do we call this light? Reflected. So we had some light reflected. Approximately what percentage? Around 4% reflected there. When the light hit here, you can see that we had some reflected inside there as well. That's another about 4%. So if I had 4% reflected here, I have 96%. Lose another 4% when you're close enough to 100%. That's still about 4% drop. So it's about 92% of the incident light here makes it out here. And the rest of that light is spread with some of it being here, some of it coming out this way. And you can also see there's a certain amount there. I'm not sure where that came from. It shouldn't be doing that. I'm sure there's a flaw somewhere in my, something, a rough surface that's causing that. Rotate it more and you see something really cool. We're starting to get some, how much light comes out here? None. No light came out. Now we're in science class, we're trying to figure out what happens in these crazy situations. Why do you think no light is coming out right here? Remember we said 4% is reflected. How much was reflected here? Why? Okay, we're past the critical angle, right? From your concept coach questions, you should have had that covered. If you get to the point where the angle of refraction requires Snell's law requires a sine theta that's bigger than 1, you've broken your math, right? Sine theta can't get bigger than 1. And so that means something different has to happen there. You can't have refraction if Snell's law says that you have to have sine theta is bigger than 1. And so the critical angle, what Carrie mentioned, I think it was Carrie, I couldn't see, so I'm going by what sound like her voice. The critical angle is the angle of incidence that will result in an angle of refraction of 90 degrees, because sine of 90 is 1. If you have an angle of incidence that's bigger than that, you simply change the domain of what's going to happen. No longer do you have Snell's law in effect, you have what we call total internal reflection. 100% of the light is reflected. None of it's transmitted. You see light on my finger here because there's light that's going above it, in case you're wondering about that. So we had light came here. What do we call the process occurring right there under my finger? Refraction. Travels in a straight line because the index refraction is staying constant. Hits here. What do we call here? Okay. Reflection, total internal reflection, just to make sure we're clear on that. Then it goes here, travels straight, gets here, and what happens here? Refracts again. This actually helps us to understand, once again, how a diamond works. Diamond has a very slow speed of light. So when the light comes into the front surface of the diamond, it's going to bend so that it comes close to going normal because it's a very slow speed. The back of the diamond is cut such that when the light hits the back of the diamond, you're going to hit at a glancing angle. So a diamond is actually cut something like this, right? So light comes in like this, goes like this, reflects. Reflects like this, and reflects around and around and around until it comes back at an angle where it can get out. So it does lots of reflections, and there's really only at these points here, I think, is where it's likely to have the angle to get out. And of course, they do a lot of work that I've never done on designing the shape to make it so you're going to have total internal reflection everywhere except for certain points, and then that concentrates light. So you only have light come out brilliantly from those if you're just exactly the right angle, otherwise it doesn't get out. So this is the process going on with the diamond. So here I'm using a prism, and you can see with the prism there's some cool stuff like, just look at the direction of the light here. What happened? Okay, I didn't hear loud enough.
It's focusing into.
Okay, it actually is focusing. Not supposed to be doing that. That's because they're not perfectly made. Good observation though. But notice as I rotate. Okay, here I have right at the critical angle, so it's coming straight down the surface. Anything more and it's total internal reflection, less it comes out. As I keep rotating, it's going closer to straight, less deviation, right? And now it's not. Now it's deviating more again as I keep rotating. Why is that? Because that sine is not a linear function, and I have two surfaces here where it's refracted. And you can go through and you can show that when the light is going through here, so you have the same angle of incident on the second surface as you had an angle of refraction on the first surface side, when it's going to be symmetric, that's where you're going to have the least deviation. Any other situation is going to give you more deviation. So this is what's going on with refraction. And you can do lots of cool things with refraction. One of the coolest things we do with refraction, of course, is to make a lens. So here is a flat surface and then a curved surface. So I'm going to have the light go in first, the curved or the flat surface. So it just goes straight in, straight through. But when it hits the curved surface, the angle of incidence on that second surface depends on how high it is. If it's up high on this curved surface, then the angle of incidence is going to be measured against a line like that. Here's measured against a line like that, here against a line like that. So can you see it all what I wrote? No. Okay, so I'm going to turn on some light so you can see. So the direction that we're measuring from is the lines I've drawn. Down at the bottom, because it's going from a slower medium, that is the plexiglass, into a faster medium, it's going away from that line. So instead of coming out horizontal, it's going away from that line and bending down. Down at the bottom, it's also going away from that line, which means it's bending up. And because I have a continuous curvature, the amount it bends depends on where I hit. And so if I have just the right shape, just the right changing in curve, I can make it so all of the light comes and meets at one point. In that place where it comes to meet, we call that a focal point. And in fact, if I have incident parallel rays, then this is the focal point of the lens. So it came to a focus at the focal point of the lens. Now, something to point out, these are ground to a sphere, well, it's cylindrical, so a circular shape, that's not the right shape. If I have parallel light, the perfect shape to have a perfect focus would be a paraboloid. Well, that's three-dimensional. If it was not parallel light, but light that was diverging or then it's ellipsoidal is the proper shape. So you actually, if you want to have a really high quality lens, you have to know where the light's coming from and where it's going and have the surfaces ground to match those. So if you have just a one object distance, one image distance, you can ground the lens that's perfect. In many situations, such as with this projector, it's made to have a range of distances that it projects to. And because of that, you actually can't grind it perfectly. And we often approximate by making it spherical, because spherical is easy to grind. But you end up with the focus not being perfect, as the light doesn't all come to a focus at the same place. And if you were to come up here and look and see, you would see, yes, this light is not all coming to a focus at the same place. Now I'm going to play with this some more next class period. But for now, I will finish just by reiterating how we do this refraction. You always need to measure your angle of incidence from the incident ray to the surface normal. I really tried to drill that in last class period. The transmitted or refracted ray is again measured from the surface normal, now the transmitted side, to the transmitted ray, and the reflected ray is measured from the surface normal. So all of your rays are measured from the surface normal. And light works the same way forward and backward. So light coming in would go like this. Light coming out, you just reverse the direction of the arrows. Light coming out would go like that. And so next class period is Wednesday. Wednesday we'll look more into this.